Okay, very good. The recording started. I take this opportunity to say that I know that I am a bit late with the recording of Monday. I will upload everything today, okay, for this week. And I want to remind you that next week I'm teaching on Monday only. On Monday we will have a regular lecturing and not on Thursday. And then we will have a break. Let me share my screen because I have 2 weeks where I am a bit busy abroad. Okay, so screen, okay, now you should see my screen. So the calendar is unchanged. Today is April 11. Okay, so I'm teaching Monday, April 22nd, and I'm teaching again Monday, April 29. So the next 2 weeks, I'm not teaching on Thursday, okay, because I am busy attending conferences. Okay, good. So if you have any question on the calendar, let me know. And then I think we can jump to a recap of what I concluded last time. I want to start with a recap of the exercise because I think the exercise it is useful in order to fully get the concept of risk computation. You know that the best thing to learn something, sorry, 1 second. Yeah, okay, this is the transcript, not the chat. I was looking at the chat and instead it was the transcript. So I saw a lot of text coming and I didn't understand because I assumed it was the chat. It was the transcript actually. Okay, so sorry for that, for the interruption. So I said I want today to make a recap of what we discussed on Monday, and I want to start from the exercise. You know that the best way to learn something is to try to apply it, to apply the something. So the best way to fully learn risk computation, which is fundamental for any action, for devising any action related to climate change adaptation. So the best way to learn risk computation is to make the exercise, and I think the exercise is highly significant. So I just want to go back to it a little bit because the conclusion was quite quick, and also I promised when I closed the lecture on Monday that I would make some considerations on the outcome from the exercise. So first of all, let me look at the text of the exercise. Now you should see it on the screen. So we don't need to reread anything. We have 2 functions for vulnerability and exposure, and then we estimated the probability of the probability distribution of river flow, which is a continuous variable. Okay, it's a continuous variable, and we estimated it into R. I just want to tell you that these river flows, the data that we analyzed, as you may remember, are annual maximum peak flows. So the experiment that I made to estimate the probability, the experiment is to pick up every year the annual max flow. Okay, this is my experiment in order to estimate the probability distribution. Actually, I estimate the probability of the annual maximum peak flow. This means that every year I pick up a probability. So if I have, for instance, the peak river flow of, say, 100, and I know that the probability of not exceedance is 0.5. This means that every year I get, with probability of not exceedance 0.5, an annual maximum peak flow that is lower or equal to 100. I say it again. Let's suppose that I pick up an annual maximum peak flow of 100. This means that if I estimate the probability of not exceedance associated to this peak river flow and it's 0.5, it means that every year I get a probability of not exceedance of 0.5 of getting a max annual flow that is lower or equal to 100. So it is the probability of the annual maximum. This is important to consider because you have to keep the connection with the process, with the problem, with the reality. So it's not a probability of getting a river flow on a given day. It's the probability of getting an annual maximum, okay, peak flow. This is important. This is the process. This is experiment. So keep always the connection with what you are dealing with, okay? Perfect. Now, I estimated this probability and then I compute the risk by the relationship R. What you clearly know, R is given by the product of P, V, and D, where P is computed with the log normal probability distribution, and we computed it, okay? And then I said, for each peak river flow, use the probability of not exceedance to estimate P, and make a reasoning on the meaning of the obtained risk values. What do they mean? Okay, now let's try to make this reasoning indeed. Okay, so if in the risk equation, this one, I use the probability of not exceedance, what is the meaning of the risk that I find? Why I am asking this question? Because when we studied this equation, I referred to a discrete random variable, a discrete random variable to describe the event, like discrete, like rolling a dice, okay? And I said that P is the probability of each outcome. Because when the event, you describe the event with a discrete number of possible outcomes, okay, it is possible to give to each possible outcome a probability. So when I roll a dice, I know that the probability of getting 1 is 1 over 6. The probability of getting 3 is again 1 over 6. And I said, let's estimate the risk by using the probability of each event. And I said, in such a way, I get an estimate of the risk associated to each event. Okay, and then you may remember I introduced these curves here. Let me just show you. Okay, 1 second that it's opening. These curves, which I called the PEVR curve, and in particular, if I look at the risk curve, the orange one here, I said there is most probably an event which gives the max risk. This is what we studied. So we assumed that the event, the possible outcomes from an event are discrete, okay, like intensity of earthquakes in the scale, in the Richter scale, 1, 2, 3, 4, 5, 6, up to 10. These are 10 possible outcomes, discrete, okay? So I can give a probability of getting any earthquake with intensity scale 8, okay? And then if the possible outcomes are discrete, I get a max with a certain intensity of the event, okay? But in the case of our exercise, and then I go back to the text, the random variable is continuous. It is continuous. It is river flow. And then I said, if instead of considering the probability of each outcome, you consider the probability of not exceedance, which is the cumulative probability, What are you obtaining here? What is the meaning of the risk? You understand that what is the difference? The difference is that in the previous interpretation, I considered only one event at a time. Okay, earthquake of scale Richter 8. I consider it perfect. I take the probability of getting the earthquake and that's it. One event at a time. Okay. If I consider the probability of not exceedance, I'm not considering just one event, but I'm considering the whole group of events that do not exceed the given one. So earthquake, scale Richter 8, probability of not exceedance. I put together all the possible outcomes from 1 to 8 because I'm considering the probability of not exceedance. So it's not one event at a time, it's the whole bunch of events that don't exceed the given one. Okay. Now, what's the difference in terms of risk computation? If I plot the result of the risk computation here by considering the probability of not exceedance, what are we getting? Okay, let's now make the exercise, okay? So to see what we get. And my suggestion for you, first of all, it's here into, 1 second, into RStudio now, okay? And in RStudio here, you see in the code window, I am reducing the size of the console to make you see the code. You see, in the code window, there is, in the code window, sorry, there is the file that I propose to you. Okay, it's here. 1 second, it's here. Suggested R code, okay, computation of risk associated to flood events. If you click there, you get this file, okay, which is in RStudio. One thing I wanted to tell you, be careful. We need to make a correction to the last line. It's already corrected on my website because here, this plot, if you tried to make it, it gives an error. We have to put here, instead of risk 1. Risk 1 is computed here, okay? So make this correction to the code if you downloaded it before. If you didn't download it before, it's now already corrected, okay? Perfect. Now let's run this code up to, so in order to run it, let me make the selection. I make the selection in the code window, but I don't want the last 2 instructions because let's wait before them, okay? Let's consider them later. Let's open a parenthesis. So let me run this one, and what I'm getting as the last plot is precisely the computation of the risk, the graph of the risk, by using the probability of not exceedance. Perfect. Let me run it. If I click on run, I am running the selection. Let's run it. And this is the risk that I get. You see, risk, river flow. It is something different with respect to what I got when I used the probability rather than the probability of not exceedance. It's rather different. It's always increasing up to the max damage that I can expect from this flood. Why it's always increasing? Of course, because it is computing the risk associated to all the events that are lower or equal to the given one. So if I get, for instance, river flow 15,000, look at my mouse here, the risk that I get is the risk given by all the events whose river flow is lower or equal than 15,000. And then if I go to 20,000, is for sure increasing because it cannot decrease. For a river flow of 20,000, I'm computing the damage given by all the events with the river flow lower than 20,000. It must be higher than the damage associated to all the events that do not exceed a lower value like 15,000. It is always increasing, okay? So it shouldn't be a surprise, because instead of using the probability of each one event, I am using the probability of not exceed. That it shouldn't be a surprise. Any questions so far? Before I move forward with the final consideration, with these last two lines of instruction. No questions. So let's assume that it's clear to you what I'm saying. Look, if it is not clear, if you are missing something, try to dedicate some time to resolve your doubts. This is a central part of our course. You will find questions at the exam about risk-based adaptation design, questions on the concept. But if it is not clear what I'm saying, it means that you don't have the concept fully clear. So I understand that you may be reluctant to make questions now if it's not clear, but if it's not clear and you don't ask questions now, please dedicate time to resolve your doubts. And if you prefer, contact me individually if you cannot resolve your doubts by yourself. Okay? Good. Now, let's suppose that instead you are interested in getting the output that I presented to you before. Let's suppose that you are, let me change the screen. Let's suppose that you want to get this risk curve. You want to get an indication of the event that gives the max risk. Okay, let's suppose that you want to get this orange curve, okay? And so far we didn't get it because we used the probability of not exceedance. And to get this curve, I have to consider each event individually, as I said. So how can we make it? For sure, it must be possible, okay? Because for sure, I mean, we are talking about a real process, a real phenomenon. It must be possible to identify a value of the river flow of the flood to which corresponds the max of the risk. It must be possible. So how to do that? Well, in order to do that, let's be very practical, because we are dealing with a continuous variable. A continuous variable has infinite values, as you know, and which means that we need to introduce the probability density and probability of not exceedance in order to deal with it, okay? And this is clear. I mean, a real variable means that I have an infinite number of possible outcomes, okay? But actually, what we did in this exercise was to discretize the variable, because in practice, when we make computations, we need to discretize the variable. Whatever software we use, Excel, R, I mean, when it's time to make the computation, the software rounds the digits up to, the description is extended up to a higher number of digits, but not an infinite number of digits. So any software for computation, at a certain point, discretizes the variable. What we do, what we did here, in fact, let me go back to the code. You may remember that we studied the probability of the river flow by studying a sequence of river flows. And we made a sequence between, look at the instruction that I selected, between 0 up to 30,000 with steps of 100. So indeed, we discretized the river flow in step of 100. If you make a plot of river flow, plot river flow, of course you get plot river flow type equal line. Of course you get a straight line, okay? Oops. you get a straight line which looks continuous, but it's not continuous. If you plot the points, type equal points, you see that it's discrete. Of course, okay, let's see. Let's limit it to the first 10 numbers, 1, 10. You see that it's discrete. So what we are studying the risk associated to discrete values of river flow from 0 to 30,000. Is this clear? So in practice, we are dealing with a discrete variable, not a real one. Good. I mean, this is what allows us to compute the curve that we want to compute the value of the river flow that gives the max risk. Okay. So how to do that? Keep in mind that we have a vector of probabilities that we estimated, which is, let me clear the screen, the console. The vector of probabilities is P river flow. Okay, this is the vector of probability of not exceedance. Let's look at the first 10 numbers. First 10 numbers are from 0 to a very low value, because indeed this is a probability of not exceedance. And of course, if I consider the low numbers, for instance, river flow 0, the probability of not exceedance is 0, clearly. Okay. If I look at the last numbers like 290, 300, because from 0 to 30,000 with step of 100, I have 300 numbers. So if I look at the last probabilities, they converge to 1, which is what I am expecting. Probability of not exceedance 1. Okay. So if I want to get the probability of each event, what should I do then? Remember that how it is defined, the probability of not exceedance. If I want to get the probability, what I have to do is take the derivative. Probability density is obtained by taking the derivative of the probability of not exceedance. So if I take the difference, diff of P river flow, and I plot it, and the plot, let's put on the horizontal axis river flow from 2 to 300. I have to start from 2 because the difference, when you take the difference of a vector, it's the number of elements in the resulting vector is the number of the elements in the original vector minus 1. Okay. So the river flow is extended from 2 to 300. And then the difference of the probability. Let's see what we get. Type equal line. Let's see what we get. Sorry. So let me see why. I think probably it's, let me see, river flow 1, 300. Okay. Sorry, I indeed, river flow, it should be extended from 1 to 300, not from 2 to 300. Or the alternative is from 2 to 301, because the number of vectors, the number of elements, the vector of river flow has dimension 301 because it starts from 0. Okay, so you see that what I obtained in the plot is the probability density. Okay, it is the probability density because it is simply the derivative of the probability of not exceedance. Now, so going to my original question, how can I obtain this curve of risk? How can I identify the max event, the event that gives the max risk? Simply speaking, I have to apply this equation by using, instead of the probability of not exceedance, the difference of the probability of not exceedance. And that's it. So what I can do is, let me go back to the code, the last two lines of the code. Let me first clear the screen. And then here, you see that according to these two instructions, I am computing the difference of the probability of not exceedance. I am multiplying it times vulnerability and exposure, and I'm plotting here the result. Let's see with the run what I obtain. And you see here what is the event that gives the max risk. It is around 16,000, 17,000 cubic meters per second. I think it is, let's put a vertical line in 17,000, vertical equal 17,000. And less than that, let's 16,000. Yeah, 16,000 is the max of the risk. And that's it. That's it. And I hope that with this recap, you got the meaning of using for risk computation the probability of not exceedance rather than the probability. I hope you got it. And if you got it, you understood the concept. If you have some doubts, once again, let's consult. Any question? Because now I'm moving to the theory. Let's call it theory. Any question? Okay. Good. Good. So let me close the PDF. Let me close RStudio. Quit session. Don't save. Good. And now let's open our page, our lecture notes on inductive and deductive modeling on climate change impact. I just want to remind you what we are talking about. We are talking about estimating scenarios of future climate in order to estimate the future probability of getting an event related to climate, an extreme event related to climate. Because I said, okay, we know how to apply the risk equation, and we know that the risk equation is essential for our design. We know how to apply the risk equation, but the good question is, how can we estimate the future probability under the future climate? And then I said we can use trend estimation and we can extrapolate trend analysis, or we can use run theory. Run theory gives me the frequency of droughts, and frequency of droughts is probability into the future. So run theory can be applied to historical data, but then if we see a trend in probability, we can extrapolate this trend into the future. And then I said, look, run theory is also important because it allows us to detect cycles, and the cycles can be confused with the trend. So clearly, if I am in the presence of a trend and I look at the future, I keep increasing in my probability of event, because if the trend is increasing, I keep it increasing. If I am in the presence of cycles, I know that in the future I may have up and downs of probability, not just merely an increase or a decrease. Okay, so indeed, estimation of cycles is important. And I said, look, sometimes these cycles may be extremely long, and they may be related to different forcings like solar activity or or disturbances like changes in the inclination of the Earth axis, changes in obliquity, and there might be changes in eccentricity of the position of the Sun with respect to the orbit of the Earth. There might be changes related to a change in precession, and precession is the secondary axis of rotation of the Earth. Okay, and I don't go into the details, but I mean, it is sometimes we have to accept the idea that there could be very long cycles. And I want to mention to you what is a possible method for detecting these long-term cycles, because you understand, if a cycle is very long and you have only a reduced sample of data, so if the sample is that long and the extension of your data is just this, how can we recognize if this part of the data, this narrow interval, is part of a longer cycle rather than something that keeps increasing? So you understand the problem. It is, how can I distinguish a trend from a cycle? And for instance, if I look at this series of the Po River, look, this is annual maximum peak flow of the Po River. You see that in some of the cases, in some intervals, you can identify a trend, an increasing trend. Like let's start from 1930 up to 1970. You see that in this part, in this time window, there is an increasing trend. But if you look at the whole series, it looks like part of a cycle, of a long cycle. You see, this picture seems that it starts from a low level and then goes up and then goes down again. So it is indeed, if you have only a small chunk of data, only a limited period of data, how can we distinguish if it is a trend or a cycle? So there has been a lot of studies on that, and I want to mention that this method, and first of all, the presence of long-term cycles in a time series, it's also called long-term persistence or long-range dependence or long memory, because it's memory that makes a cycle. Now, how can we estimate then the presence of long-term persistence? Okay, so this is something that, let me increase the size of the font. This is something that you don't have to learn by memory, but I am much interested in you learning the concept. I am interested because I think it is a concept that helps you to improve your skills in understanding what's going on in reality, nature, okay? So the method is very simple and is based on computing the variance of the data. The variance, remember, is like the standard deviation. It's the square of the standard deviation, okay? So if let me open a graphic window and I show you what I mean precisely. And okay, let me just open it. Okay, and let me put it on the screen here. Okay, perfect. This is my graphic window. And let's suppose that we have this time series of data, okay? And this is the time axis. This is the time axis T, okay? And then let's suppose that I have here a graph of whatever variable, okay? So let's suppose that it's something like this, okay? And I am very rough in drawing it. Sorry, this is not good because I went back. Again, I went back. So let me try to be more. Okay, this is something that it's maybe temperature because it's smoothly varying. Okay. Okay, let's suppose that we have this time series, this plot. Okay. And now let's start with the idea of taking a window with size n, okay, taking this window, and the size of this window is n, okay, it's n, meaning that the number of data inside this window is n, and let's compute the variance here, okay, so we compute the variance of the data. 1 second here, compute the variance. This is too big. Let me see if I succeeded in getting, yes, compute variance. Okay, we compute the variance of the data. And the variance, again, it's the square of the standard deviation. So you know what is, okay, because you can compute it in R very, very easily. Now, of course, in a short time window, you expect that there is a lot of variability, and but a lot of variability, but not too much. I mean, if you, for instance, look at the temperature in January, you have some variability, but if you take a longer window, like temperature in the first 6 months of the year, the variability is larger because in January is more or less constant, the temperature. But then when you get in May, it's higher than in January. And therefore you have more variability. So you expect that the variance, which is a measure of variability, increases as you increase the number of data. Okay. And look, what is your expectation? Your expectation, however, is that if you have cycles, you get more variability with respect to a normal situation, because cycle means long up and downs. Okay, and instead, if in the absence of cycles, the data are more compressed around the mean. Okay, so you understand that the progress of the variability, the progress of the variance for increasing length of the window of computation may give you an indication of the presence of cycles or not. And indeed, this is what we want to study here. So I compute the variance of the average of this data over a window of size n. Average, I didn't say average so far. So let's, this is important. I don't compute the variance of the data, but the variance of the average, which is, of course, as I increase the size of the window, is increasing, okay? Because I basically, the longer the window and the more variable becomes the average, okay? And then basically, I can write this, there is a theoretical demonstration that says that the variance of the mean increases with increasing the size, the number of the data, with increasing capital N, according to this law that you see here. So it's a power law, okay? It's a power law. And it can be proved that if this exponent h is equal to 0.5, we don't have long-term cycles, while for h larger than 0.5, and less than 1, because it can be proved that we can't get h larger than 1 for reasons that we don't discuss here, we have long-term cycles. And the intensity of long-term cycles, so I mean the strength, the length, and the amplitude of these cycles is proportional to h. So h 0.5, no cycles, h larger than 0.5 cycles. And this is based on this very simple computation. H is called the Hurst exponent, which is a measure of these long-term cycles. This is the link that I clicked on Wikipedia. You see here, the Hurst exponent is used as a measure of long-term memory of time series. What is long-term memory? Long-range dependence, also called long memory or long-range persistence, is a phenomenon that may arise in the analysis of time series data. It relates to the rate of decay of statistical dependence. It's related to cycles. Okay, if you look here, and you see that it is also explained that is related to cycles. So what is the reason why, let me go back here. What is the reason why I'm mentioning this to you? Because I think, first of all, this is very relevant. When we talk about future climate scenarios, this is a very relevant phenomenon to understand whether climate may be cyclical rather than, in a way, monotonically increasing or decreasing. This is very relevant. Indeed, the presence of long-term dependence in climate is highly debated in the scientific community. So it may happen to you, if you deal with climate change, that you get to hear about the Hurst exponent or long-range dependence. Okay, and therefore this is why I wanted to make you aware of it with a very simple treatment. You again, you will not get any question in the exam related to this, okay? But on the other hand, beware, my suggestion, beware of it, because it's extremely important. Now, it is interesting, I'm not sure if I already mentioned this to you, how long-term memory, long-range dependence was discovered by Harold Edwin Hurst, the guy after whom the Hurst exponent was named. Harold Edwin Hurst was an engineer, a British engineer, and he was an engineer designing dams along the course of the Swan River. And when you design dams, you have to estimate their storage, the required storage. And the required storage, you understand that it depends on the presence of cycles, because the purpose of a dam is to transform an irregular inflow into a constant outflow. The purpose of a dam is to store water when it is in excess in order to be able to use water when we are in scarcity. So the purpose of the dam is to store, and the required storage in the presence of cycles is larger. Is larger because a cycle, it means that I have a long period where I have excess water and a long period where I have water scarcity. So I need a larger reservoir. So Hurst was studying the size of the reservoirs, and therefore he was puzzled because he discovered that the size of the reservoir, the result of its size estimation, storage estimation, was not as he expected. So he discovered this phenomenon, long-range dependence, and his discovery, which happened by chance, was a game changer in reservoir sizing, and now we can say a game changer in climate change adaptation. And indeed, I think the history of this discovery is interesting because it gives to you an example of how, while working a simple intuition may turn into a big discovery. And you may make the same example by referring to the relativity theory by Albert Einstein. I mean, sometimes the game changer discoveries happened by following a very simple intuition that must be associated to a high level of creativity. I mean, a high desire to resolve the doubt. Like, you, at a certain point, you don't understand something, and you have the intuition that this something is, there is no current explanation for it. And then you are motivated to try to find it. So it's a motivation to resolve something that you don't understand. And this may lead to a great success. And this is why I'm telling you, I told you even half an hour ago, if you have some doubts on the concepts, be motivated to resolve them, because it is this motivation that brings you towards a successful career. And the history of Earth is briefly described in a presentation that I prepared for a seminar to PhD student. And this presentation, it is very easy. Let me open it because I want to show you, because it's not something that you should look at for your exam, but I still think it is interesting because it's there is also R code that you can apply to understand what Earth discovered. Basically, the R code is the estimation of the size of the reservoir, and it is based on the same approach that we engineers use to estimate the size of the reservoir. And basically, it is illustrated here that Earth basically didn't get what one would expect. Okay, and here one would expect that the required volume after a certain period stabilizes, and Hurst found that for increasing length of the observation period, indeed the size of the reservoir kept increasing. And this is, he didn't understand why, and he didn't want, he wanted to resolve this doubt. And then basically he made this big discovery. Okay, let me close this. And now with inductive estimation, because this is still inductive estimation, you see this formula here, we are analyzing data. We are analyzing data and try to understand from the data how the future will be. So we analyze historical data and try to understand, again, from the data, from the outcome, how the future will be. But at the beginning of this lecture, I said that we have two alternative approaches, inductive or deductive estimation. Inductive means that we use data. Deductive estimation means that we use models. So let's now focus on the deductive estimation using models, which in a way is perhaps more fascinating than analyzing data, because if you use a model, basically you, in a way, you estimate what the future will be basing on your understanding of the mechanism of the process, which is, I mean, it is, yeah, in a way more fascinating. Keep in mind that usually it's more complicated. So statistics looks complicated, but it's much less complicated than writing a numerical model of the climate system, or even simple numerical models, even without considering the whole climate system. But if you consider, for instance, we will talk about models of rivers, describing the river flow, or we can talk about models describing the mechanisms that lead to the formation of earthquakes. These models are extremely complicated, much more than statistical analysis. In fact, sometimes in science, some people consider the statistical analysis like a surrogate, like something that it's not very scientific. I don't agree. But what I want to say is that sometimes we are more fascinated by models, by process understanding. But if we look at the technicalities, if we look at the difficulties, it's much more difficult to apply a model than making a statistical analysis. I just want to mention to you that recently, I'm sure that you are aware of it, there has been an increasing interest, and I would say an increasing fashion for machine learning, deep learning, artificial intelligence. And they are to some extent synonyms. I would say that artificial intelligence is, to my view, a little bit more than machine learning, but not really that more. So machine learning is learning from data, and you study the data and you elaborate the data through an automatic algorithm that studies the regularities in the data, studies the patterns of the data. And machine learning is not much different from statistical analysis, because also statistical analysis can be considered part of machine learning. And machine learning has been introduced to, the terminology has been introduced to emphasize that the learning is done by a machine rather than a human study of the data. So statistics may be considered a human study. Actually, we make statistics by using machines, but of course, it was born when machines were not there, so it's considered to be a human study made by humans, while machine learning is made by machines. So machine learning can use more computational power, uses more computational power usually. And this is why we call it machine learning. Artificial intelligence is doing something more, because it is involving several techniques of machine learning put together with some original algorithm of distillation, algorithm that put everything together, make a synthesis. But it's not much different, and the term became very popular after the introduction of ChatGPT, which is machine learning applied to text and information taken from the web by chance. So basically, ChatGPT goes over the web, while machine learning was normally applied to an assigned database, to assign data. Artificial intelligence and in particular ChatGPT just goes over the web and analyzes everything that it is found there. So the news was the machine learning applied to the web, not really the concept, which was already known. Of course, ChatGPT has some problems, as you know, like a copyright violation, or it was already sued by several newspapers because it doesn't respect the copyright, or by extracting the information without making a preliminary selection of the database, the information that is extracted may be less reliable. But I mean, what I want to say is that the popularity of these methods, which increased a lot in the recent 2-3 years, and it is amazing to see how in science as well, these methods have increased in popularity. On the other hand, it is not really a news. It is something that was already available. I think that it's the reference to the entire web that was innovative, but I mean, it is something that we don't discuss here, but we can use for sure, and people already use machine learning in order to make prediction of future climate, artificial intelligence in order to make prediction of future climate. Keep in mind that it is something that climate scientists they are not unanimous in considering this approach of machine learning, artificial intelligence applied to climate a good approach, because they prefer to use the deductive estimation. Artificial intelligence is still inductive, even if when there are in any classification you have a gray zone. So some people think that artificial intelligence may also find over the web a model in order to make a prediction, and therefore it becomes deductive in that way. But usually, I mean, the typical outcome that you get from artificial intelligence is inductive. Now, let's focus then on the models, on the deductive estimation. And again, I made some consideration on machine learning, artificial intelligence. It's not in my lecture notes, so it's not for your exam, okay? So deductive estimation of climate change, modeling. So what kind of models do we use? We already made an introduction when we talked about the Earth system. And basically these models want to describe the climate system. And so they are models describing storage and flow of physical matters, most of them. And therefore, they are based on conservation equations, which I think we already discussed. Conservation of mass, energy, and momentum are frequently applied. And these conservation equations very often need to be specified in differential form. So these models are made by a composition, as we already discussed, of differential equation. And very often they are partial differential equation, because they want to describe the dynamics of these processes in space and time. And in particular, global climate models, they need to describe the variable of interest in space and time. Okay, now let's say some more about climate modeling. First of all, I'm not sure, I already mentioned to you that the predictions by climate models can be easily retrieved from several public repositories. And one interesting example is the Copernicus Climate Data Store. It is not easy to use this repository. In general, keep in mind that these models results involve a massive amount of numbers, a lot of numbers. And therefore, managing these millions of data, and you understand, they have to describe the climate at the global level. So the spatial domain is the whole Earth system, and the temporal domain is long, because they start their simulation from 1850, and then they go forward up to 2100. I mean, it's a lot of numbers. So managing these numbers, it's not easy, and even retrieving them, it's not easy, because these are huge databases, and you need to use codes in Python in order to retrieve the data. So this is anyway what we need to be aware of, that on the web there are climate projections, and there are also what we call hindcast, a reconstruction of past hindcast. I don't remember the pronunciation. I think it is hindcast. It's a reconstruction of past climate. The term that I wanted to say is this one, hindcast. And let's you see here, I took the first link, so it's not opening. Anyway, it's reconstruction of past climate. It's here. And in the realm of meteorology, oceanography, and climate is a methodological approach used to simulate and analyze past weather or ocean conditions. Okay, perfect. And let me close this. So these past reconstruction are useful because you can test the models. You can get an idea of model uncertainty, model reliability. And in fact, you have to always take into account uncertainty of these model simulations. We discussed it several times. And in order to quantify this uncertainty, a useful approach may be indeed to look at a reconstruction of past climate. And in general, this reconstruction allow us to correct the bias of models. Bias means that if you compute the average of the historical data and the average of the model simulation, there is a shift. And this shift in average is called bias. The bias may be a seasonal bias, so varying along the seasons, may vary in space and time then, And therefore, a usual procedure is to correct the bias. So I wanted to introduce this terminology to you because bias correction of climate models is a topical issue. It's a topical issue that is frequently mentioned. And as I said, we need to correct it, because when we see that in the reconstruction of the past climate, the average value is not well reproduced, this is something that we cannot tolerate, because at least the average computed over a time window we know of at least 30 years need to be preserved. So when we see a shift in the average, we need to correct it. What is the simplest way of correcting a bias? The simplest way is to use the climate models to simulate not the future climate, but the future climate change. So instead of simulating the temperature in 2050, I use the model to simulate the change of temperature between now and 2050. And simulating change is the easiest way to eliminate bias. Okay, because if I simulate change, I start from the current value of climate, of the average climate. So the bias is adjusted to the current value, and then I project the change. And this is what it is usually done, okay? Another thing is that you have to consider that the bias uncertainty is different depending on the variable. Be aware of that. So if you correct the bias in temperature, don't take for granted that automatically you correct the bias in rainfall. It's not like that. You have to individually correct the bias, individually estimate the uncertainty for each variable. Okay, so you understand the complexity. But now, I don't want to mention again climate models because they are too complicated. Let me make a more specific example. Let me make reference to floods or droughts. So let me make reference to river flow, because in this way I can illustrate to you in a simple way examples of models. So let me give you some examples, because these models, actually the concept is very simple. It is when you put them together in a numerical form that you get very long equation, you get a huge number of equations with a lot of effort that are needed in order to fit these models, fit to purpose. But the concept in itself, if you isolate single processes, it's quite simple. So let's refer to river flow. And river flow is a part of the climate system. I mean, water cycle, as you know, is a part of the climate system. And what is the terminology that we use for these models of river flow? So the river flow is a system that gets water typically from precipitation, rainfall. Precipitation actually includes rainfall and snowfall, but usually we can use in technical setting, the term rainfall is often used as a synonym for precipitation. So a river system takes water in the form of rainfall precipitation, and it transforms the input, rainfall, into an output that is river flow. Okay, so we call these models rainfall runoff models. It's one of the most classical applications in hydrology. So what is the purpose of these models? To simulate river flow, the progress of river flow in time. Keep in mind, the progress of river flow in time is also called hydrograph. If you look at the link on Wikipedia, this is an example of an hydrograph. Stream flow, which is a synonym of river flow, against the Julian day. And keep in mind that the river flow may be called the stream flow, may be called river discharge. There are several synonyms. And usually the river system takes water from a selected area. Okay, so let me just look for a figure. So images. Okay, so this is, let me take the best one. Let me see. I think that the best one is this. Okay, let me just, let's look at it here. Okay, so you see that the river is getting water over a given portion of the land, over a given area, which usually is estimated by following the mountain divide. So you see here the dashed red line following the divide. The divide is the line of separation of water flowing on one side of the mountains, of the mountain, rather than the other side. So you follow the divide of the mountains and you identify the area that is collecting the water that forms the river flow. And this area is called catchment or watershed. It depends on the American or UK English. In UK, they use more frequently the term watershed, but historically, but in the modern terminology, I see more frequently catchment. Another synonym for catchment or watershed is river basin. Okay, and other examples you see here: the divide over the mountains, and then the watershed, that is the area that collects the precipitation that goes into the river. In this figure, you see that it's highlighted the presence of humans, because now you know that we understand that humans have a strong influence on climate and on river flow. Then this is another picture. So it's another figure of a catchment, and here you don't see in explicit the divide, but you see the whole representation of the water cycle. The catchment or watershed is usually the computational domain of rainfall runoff models, because it is the control volume. It is the volume over which the rainfall runoff transformation takes place. We assume that it's a closed system, while actually it's strictly speaking it's not, and we model it by using these conservation equations. And let me see, there is let me see if I find it. There is a figure of the USGS of the water cycle, which shows, let me see if I can find it, USGS hydrological cycle. Let's see if we can find it. Yeah, this one, I found it. let me visit the website, because I want to take the I want to make it large. So you see, this is a more complicated description, which includes the watershed or catchment, and then describes the presence of humans, and describes also the groundwater part of it, which is the below ground portion of the watershed, of the catchment. And this shows that actually we are talking of a volume. The land surface is an area, but if you include also the portion that is underground, it becomes a volume. Okay, so rainfall runoff modeling. This is another very popular figure of the water cycle that we need to describe. I mean, if we want to describe river flow, we need to describe this water cycle. And of course, we can make simplifications, and we can describe only part of it. And in fact, rainfall runoff modeling is a very old discipline. The first model, rainfall runoff model, was introduced around 1860. And we will see this model. It's very simple, and it means that they didn't have any computational power. They needed to make several simplifications in order to run the model. So let's see this model. This first model that was introduced in 1860, which is, I think, highly illustrative and also highly used in order to make predictions of the future, also future predictions. And this model is called the rational formula. And the rational formula gives an estimate of the river flow for a catchment with area A. Okay, and look at the units. The river flow is defined, we take a river cross section, so a location along the river, and the river flow is defined as the volume of water per unit time passing through the river at the given location. And therefore the unit is volume, length cube, length L, capital L stands for length cube, per unit time t, and the unit then is length cube divided by time. And of course we need to identify a catchment. We indicate with A the area of the catchment. The unit is L square, and then we need input data. Input data is rainfall, of course. And we describe rainfall through its intensity. So we assume that over the catchment, a rainfall happens with a given intensity. Intensity means depth of water, of rained water divided by time. So the unit of intensity, rainfall intensity, is length divided by time. And we introduce what we call a runoff coefficient. What is the runoff coefficient? We understand, they understood in 1860, that not all the rainfall is converted into river flow, because you understand there are losses. For instance, think of a catchment, the roof of your house. You don't have many losses there, and therefore all the rainfall is converted into flow over the vertical pipes that bring the water away. Okay, no losses. But if you think of a natural catchment, there are losses. What are these losses? Evaporation, for instance, transpiration by plants, or water that may be lost for deep infiltration. So it goes into the earth's interior and then it comes back maybe after years. So these losses are simply estimated by reducing rainfall. And how do we reduce it? By multiplying rainfall intensity times a reductive coefficient. A reduction coefficient is the runoff coefficient. The runoff coefficient is included in the range 0, 1, extremes included. For the roof of your house, the runoff coefficient is close to 1. For a very arid area like the Sahara Desert, it's very close to 0. Okay, so basically the rational formula is, simply speaking, just 1 second because I wanted to enlarge it. It's given by the product by runoff coefficient times rainfall intensity, C times high, which is what we call net rainfall. It's rainfall without the losses, times the area of the catchment. If you think at the units, runoff coefficient is dimensionless. Rainfall intensity is length divided by time. Area is length square. The result is length cube divided by time. So it is dimensionally consistent. It is a very simple computation. So you take the rainfall flowing over the catchment, you remove the losses, and what remains there is transformed into river flow. It's a conservation equation. Do you understand that? It's a conservation of mass with a term that takes into account the mass losses. Mass of what? Water. Mass of water. It's conservation of the mass of water. Here, I didn't highlight the dependence on time. Actually, usually river flow depends on time. And actually, rainfall depends on time. The runoff coefficient is assumed not to depend on time. Why I didn't put the time here? Because the rational formula is appropriate for describing the peak flow, not for describing the full hydrograph. And therefore, in order to avoid confusion, it's preferable that we omit the dependence on time. If you look at the textbooks, they usually omit the dependence on time. So rational formula, if we look over the web, let me just get a Google page, a rational formula. Let's call it here. Search it here, rational formula. So rational formula for discharge. See here, this is I think it is an institutional website of the state of Maine. Okay, and here you see that there is the rational formula here, QCIA, and where Q is the peak rate of runoff. Peak rate of runoff means river discharge. Peak. What is important is peak. Runoff coefficient. So it is precisely the same link. And here, another link. This is from an engineering company. It's, you see, this is a calculator, but we don't need it. And the rational equation, look here, is the simplest method to determine peak discharge from drainage basin runoff. Okay, let's go back to my website. And so it allows an estimation of the peak. Why it is not good for the estimation of the hydrograph? Because as you see here, we put rainfall intensity and the river flow is estimated as a linear function of the rainfall, because C and A are constant. So this is a linear function. River flow is a linear function of rainfall. This is quite a crude approximation. First of all, it's quite rough. And second, here there is no simulation of storage, no simulation of storage into the catchment, which means that, I mean, if you don't simulate storage, how can you simulate the progress of river flow in time? Here, river flow, it is simulated as a fraction of rainfall. And there is no simulation of storage, and therefore, I mean, the progress in time of river flow cannot be simulated, because if you don't consider storage in natural basins, there is storage. You may say, and what about the peak flow then? We can't describe the peak flow if we don't consider storage. Actually, when you get to very extreme flows, the effect of storage in catchments is negligible. Because when the catchment is full of water, is completely overflowing, there is no storage anymore. And all the rainfall that rains over there is transformed in river flow. The storage is active at the beginning of the event. When the catchment is still dry, rainwater is absorbed by the soil, by the catchment in general, by the plants, and therefore there is the creation of storage. But once that the catchment is has the storage exhausted, it's completely full of water, then the extreme flow can be expressed indeed as a fraction of rainfall. Any additional rainfall is estimated, is produced as river flow. And therefore, this is why the rational formula is used for estimating the peak, okay? Learn the rational formula. This is a classical question at the exam because it's very simple. So just learn it and try also to understand how it works. Try to understand the concept. Now, a question here. How can I estimate rainfall intensity? This is the issue because, if I have data, I can use the data. But if I need to make a design, I need a design value for rainfall, and we don't get into the details. Let's assume here there is an indication, a discussion on that, and how to estimate rainfall. But let's forget about it for now, and let's assume that we use historical data for generating this river flow scenario. However, there is one concept that I want you to learn, the concept of return period. Okay, here is defined by referring to rainfall. We already discussed the return period, I think, but the return period is something that is very relevant to climate change analysis. And what is the definition? As you can read there, the return period is defined as the average time lapse between two consecutive events with, in this case, rainfall intensity reaching or exceeding a given threshold. But you can apply the concept of return period also to river flow. And please learn this concept, this definition. There is a lot that you can find on the web on the return period. And the return period is proportional, as you can understand, to probability of not exceedance. It can be expressed as a function of the probability of not exceedance, because the return period is proportional to frequency, and you know that frequency is probability, is a synonym for probability. So very often you will listen something like climate change is changing the return period of extreme events, or you may hear something like we need to design the bridge for a return period of 200 years. This is what usually the legislation suggests. The legislation in engineering imposes the return period, the design return period of certain structure and infrastructures. So for instance, for river levees, for river bridges, it's the legislation that is fixing, at least in Italy, but also in Europe, is fixing the return period. And also in the United States, several legislations, they use the concept of return period in guidelines for technical design. So please learn this, okay? Even if you are a non-engineering student, learn what is the return period. Okay, there is one last thing that I just wanted to tell you, and you get additional details here. When you put rainfall into the rational formula, when you plug in rainfall, you have two options. Either, as we said, use historical data. Another option is when making design, typically, you put there an artificial rainfall. A rainfall that is usually an extreme one. Artificial because we want to make the design with respect to a reference context, which is typically the context of an extreme event. I want to design a bridge for a river, and then the legislation tells me that the design is to be made by assuming a return period of 200 years, I said. Okay, perfect. Now, if the recommendation is that the river flow should be estimated with a rational formula for a return period of 200 years, what kind of rainfall should I plug in there? There is an assumption behind the rational formula. The return period of the river flow is the same return period of the rainfall. So the rainfall that I have to plug in into this formula is the rainfall with the same return period of the river flow. This is the first consideration, so please remember it, and it's written here in my lecture notes. Second consideration, when I refer to a rainfall event, extreme one, there are two features that I need to specify in order to identify the event. The first feature is the return period. The second feature is the duration of the rainfall. Because it's not the same thing, a rainfall that for a given intensity lasts for 1 minute or lasts for 1 week, you understand? So I need also to specify the duration. What is the duration of the rainfall that we plug in into the rational formula? It can be demonstrated, and we don't demonstrate it, that the duration of the rainfall should be the same of the time of concentration of the catchment. And here is defined the time of concentration. It is the time required to water from traveling to the divide to the river. But this definition that I just gave is not rigorous. Please read the rigorous definition, which is here. The time of concentration is defined as the time needed for water to flow from the most remote point in a watershed to the watershed outlet. And so remember, please, because it may be also a question for the exam, definition of return period and time of concentration and rational formula. They are all related. I stop here. Any question? Okay, good. So I think 1 second. Stop sharing and close the registration. Stop recording. Okay, I will put